All right, this is another optional video that you can watch. This is for any of you that may are struggling a little bit with stoichiometry. The first couple of problems deal with just general stoichiometry problems, and then I believe there's a couple at the end that deal with limiting and excess reactants as well. So if you're struggling with either just regular stoichiometry, or if you're having a hard time understanding limiting and excess reactants, this may be a good opportunity for you to get a little bit more understanding about that. So we're just going to go over some problems together, and then we'll hopefully you'll get a little bit more comprehension out of this. So the first question says, what mass in grams of hydrogen is needed to produce 200 grams of NH3 from its elements? Okay, so first of all, we got to think a little bit about this. We are going to be forming NH3. We're going to be producing NH3 from its elements. So we're going to be producing NH3 from its elements. So what is the elemental form of nitrogen? It is a diatomic molecule, so it's N2. And then what is the elemental form of hydrogen? Also a diatomic molecule, so it is H2. So there's our equation. Now we need to balance it. I see two nitrogens on the left, two nitrogens on the right now with that 2 there. And that makes 6 hydrogens on the right, so I need a 3 right here on the left. Okay, what mass in grams of hydrogen is needed? So they want to know how many grams of H2 is needed to produce 200 grams of NH3. So one of the things that we have to assume here is we have to assume that we have extra nitrogen. Now that we've talked a little bit about limiting reactants, we're going to assume that we have plenty of nitrogen and we're only worried about hydrogen at this point. So we're going to start with the information that they give us. We always have to start with a number, 200 grams of NH3. When we have grams of NH3, the only thing we can convert to is moles. So NH3 has a molar mass of 17 grams per mole. And then from our balanced equation, we're going to go from moles of NH3, and from our balanced equation, we see that there's a 2 in front. So 2 moles of NH3 are made from 3 moles of H2. And now our final step, 1 mole of H2 has a mass of 2 grams. So now if we've done this correctly, everything will cancel except for what they're asking us about at the end. And now we can take 200.0 grams, divide it by 17, multiply by 3, divide by 2, and then multiply by 2. And my final answer comes out to be 35.3 grams of hydrogen. So again, the question was, how much hydrogen do you need to make 200 grams of ammonia? You only need 35.3 grams of hydrogen. Now, they don't ask us this, but they actually could say, all right, how much nitrogen do you need as well? And this is one where we could actually just use logic. If we have 200 grams of product, according to the law of conservation of mass, if we have 200 grams of product, we have to have 200 grams of reactants. So if we have 35.3 grams of hydrogen, we could say, all right, the amount of nitrogen you need would have to be 200 minus 35.3. So the amount of N2 you would need would be 164.7. And if we actually did the math, if we did this same process, but to get nitrogen instead of hydrogen, we actually would have gotten that answer as well. If you would like to check that, you certainly can. But we know that those two here have to add up to the mass of the products as well, according to the law of conservation of mass. Okay, our next question says zinc reacts with sulfuric acid to produce zinc sulfate and hydrogen gas. What mass of hydrogen is produced from 31.8 grams of zinc? So we've got Zn, zinc, reacting with sulfuric acid. Sulfuric acid comes from sulfate. Sulfate has a charge of -2. So we have 2 hydrogens to cancel that -2. It's going to make zinc sulfate. Zinc always has a charge of +2. So the formula is just ZnSO4 and hydrogen gas H2. Okay, let's check and make sure that we're balanced here. And just a quick look, 1 zinc, 2 hydrogens, 2 hydrogens, SO4, SO4. We are balanced. There's nothing we need to do to balance this. So the question is, what mass of hydrogen is produced? So they want to know how many grams of hydrogen is produced from 31.8 grams of zinc. Now again, we know this is not a limiting reactant problem because they're not giving us any information about sulfuric acid. So again, what we have to assume here is that we're going to have extra sulfuric acid. That's not going to be the one that runs out. So then we can just take 31.8 grams of Zn. We need to go to the periodic table here. Zinc has a mass of 65.4 grams per mole. And then from my balanced equation, there is 1 mole. Notice there's no number in the front, so it's a 1. 1 mole of zinc is going to make 1 mole of hydrogen. And then 1 mole of hydrogen has a mass of 2 grams. And if we've done this correctly, grams of zinc cancel, moles of zinc cancel, moles of hydrogen cancel, and all we have left are grams. And obviously that's grams of hydrogen. So then we can just take 31.8, divide it by 65.4, times by 2, and we get a final answer of 0.972 grams of hydrogen. It seems kind of weird. You've got over 30 grams of zinc, but of those 30 grams, you're only going to make less than a gram of hydrogen. So clearly, not very much hydrogen is being made. But part of that reason is because zinc is really, really heavy, whereas hydrogen is not. That's what really makes that big difference there. Okay, let's see. What mass of chlorine gas will be needed to react completely with 85.8 grams of potassium iodide in a single replacement reaction? So now we're kind of having to think a little bit about what's going to happen in this reaction. You're going to need chlorine gas. Chlorine is a diatomic molecule, so it's Cl2, to react completely with 85.8 grams of potassium iodide. That is Ki. And that's all they really tell us. They do tell us it's going to be a single replacement reaction. So hopefully we remember that in a single replacement reaction, the one that's by itself is going to kick out the other one. In this case, because chlorine is a nonmetal, it's going to kick out the nonmetal. So we're going to get K to be with the chlorine. Potassium is +1, chlorine is -1, so it's just KCl. Do not put KCl2. Because just because there's a 2 here on the left side doesn't mean you have to have a 2 on the right hand side. When we balance it, that's where we will solve that problem. So the chlorine kicks out the iodine, so now the iodine is by itself. It is also a diatomic molecule, so when it's by itself, there are always 2 of them. So now we can go through, now we can balance it, and we can get everything the same on both sides. So let's take a look. We've got 2 chlorines on the left. I only see 1 chlorine on the right, so I'm going to put a 2 there. That makes 2 potassiums on the right as well, so I put a 2 right there, and now it is a balanced equation. Okay, so now let's look at the question. What mass of chlorine? So they want to know how many grams of chlorine are going to be needed to react with 85.8 grams of Ki. Okay, so really all we're doing, it's kind of like a limiting reactant problem, but all that we're doing here is we're converting from grams of one reactant to grams of the other. So 85.8 grams of Ki we have to convert grams to moles. So potassium has a mass of 39.1 plus iodine, which has a mass of 126.9. I get a mass of 166 grams in 1 mole of Ki. And then from my balanced equation, 2 moles of Ki, here's our 2 right there, are going to react with just our 1 mole of Cl2. And then 1 mole of Cl2. Chlorine is 35.5. There's 2 of them. That makes 71 grams. So now we're done. Everything should cancel out. Grams of potassium iodide, moles of potassium iodide, moles of chlorine. All we have left is grams of chlorine. So we're going to take 85.8 divided by 166 divided by 2 times 71 equals 18.3 grams of Cl2. So again, what that's telling us is that for all of this potassium iodide to react, we only need 18.3 grams of chlorine. Think about like a business that's a chemical business that's trying to produce stuff. Of course, guess what? They're going to be using stoichiometry so they can figure out exactly how much stuff they need so they're not wasting money on other chemicals that are just going to be left over. So they use equations just like these to convert from grams of one reactant to grams of another reactant. All right, here's another one. This one is dealing with limiting reactants. So if you need help with limiting reactants, this is a good question for you. It says, how many grams of carbon dioxide can be obtained from the reaction of 100 grams of sulfuric acid and 100 grams of calcium carbonate? So they're giving us some information here. Let's see if we can write out that balanced equation. So we've got sulfuric acid, H2SO4, and we've got calcium carbonate, CaCO3. Now this looks like a double replacement reaction. It looks like the H2 is going to go with the CO3 and the calcium is going to go with the sulfate. So when the calcium goes with the sulfate, calcium is +2, sulfate's -2, so it's just CaSO4. Now in this case, and I'm not sure we've talked about it in this class, but when H2 goes with CO3, what it should make is it should make H2CO3. When you form H2CO3, though, what you really do is you break that apart and you make it water and carbon dioxide. So that's where that carbon dioxide comes from. So instead of H2CO3, what we write is we write plus H2O plus CO2. And then we can answer the question that they're asking us. All right, so the question is, how many grams of CO2? So they want to know how many grams of CO2 can be obtained from the reaction. So you got 100 grams of sulfuric acid, and you got 100 grams of calcium carbonate. So we know this is a limiting reactant problem because now they're giving us information about both reactants. And we have to figure out which one's going to run out first. So it doesn't matter which one you start with. Let's start with our 100 grams of H2SO4. H2SO4 has a mass of 98.1 grams from the periodic table. And then I believe this, I should have checked, I didn't. This equation, just real quickly here, it looks like it is already balanced, so we don't need to do anything. So from the balanced equation, 1 mole of H2SO4 is going to react with 1 mole of calcium carbonate. And calcium carbonate, let's see here, calcium has a mass of 40.1 plus 32.1. And 16 times 4 is 64, so plus 64. Calcium carbonate has a mass of 136.2 grams per 1 mole. So then our grams of sulfuric acid are going to cancel out. Our moles of sulfuric acid are gone. Our moles of calcium carbonate are gone. And now again, we're back to the math. So 100 divided by 98.1 times 136.2 gives me an answer of 138.8 grams of CaCO3. Now, what we find, now we need to compare. So we've got 138.8 grams of calcium carbonate. In order to react with 100 grams of sulfuric acid, this is how much calcium carbonate you're going to need. This is how much calcium carbonate you actually have. So you need almost 139, but you only have 100. So that's telling you that we don't have enough calcium carbonate because we need more than what we have. So we know that calcium carbonate, this is our limiting reactant, and therefore sulfuric acid is our excess reactant. So when we're actually answering the question, now we know we're going to use the limiting reactant. That's the one that's going to make the reaction stop. So let's go ahead and do our next part here. So since we know that calcium carbonate is the limiting reactant, we're going to use that. So 100 grams of CaCO3, and then we want to convert those grams to moles. Up here we found the mass already, 136.2 grams in 1 mole of CaCO3. And then again, balanced equation, 1 mole of CaCO3. And then here's our CO2 over here. It's going to make 1 mole of CO2. And then 1 mole of CO2 has a mass of 44 grams. So now we take 100 divided by 136.2 multiplied by 44 equals 32.3 grams. Okay, and that's how much carbon dioxide you would get. And that's how, and once you use those 100 grams of calcium carbonate, the reaction is now over. It's done because there's no calcium carbonate left, so there's nothing for this sulfuric acid to react with. Okay, if you messed up, if you thought that sulfuric acid was going to be the limiting reactant, what you would find is it would be, let's see here, let me just do the math here real fast. What you would have gotten is you would have found that it was going to make 44.8 grams of CO2. Okay, if you use the excess reactant, your answer is going to be too high because you're not going to use all 100 grams of this H2SO4. You're going to use the 100 grams of calcium carbonate, but again, once those 100 grams run out and you've made 32.3 grams of carbon dioxide, the reaction is done because you don't have any more calcium carbonate left. All right, let's see. I think, yeah, this is the last one right here. So again, this is another limiting reactant problem. So it says, in testing for the efficacy of an antacid compound, 5 grams of hydrochloric acid is mixed with 24 grams of magnesium hydroxide. Magnesium hydroxide, Mg, parentheses, OH2. And then it says, is this enough base to react with all of the acid? So again, this is kind of a limiting reactant kind of problem. So first of all, we have to figure out our ratios here, so we have to finish this equation. We've got a positive and a negative and a positive and a negative, so this is a double replacement reaction where the positives are going to switch places. So the magnesium goes with the chlorine, and when it does that, magnesium's +2, chlorine's -1. So you get MgCl2, and then when you have hydrogen and hydroxide, you always get water. Okay, now it's definitely not balanced, so let's get the balancing part going here. Let's get rid of all this extra stuff. Okay, so we've got 1 hydrogen on the left. We've got 2 hydrogens on the right. So let's put a 2 right there. That makes 2 chlorines. 2 chlorines. We've got a magnesium. And here we've got 2 oxygens. Oh, I didn't count those at the beginning. Or 2 hydrogens. I forgot to count those, but it looks like we need a 2 right here. Now we've got 4 hydrogens. 2 plus 2, 4 hydrogens. And then our 2 oxygens. 2 oxygens. It's balanced. All right. So now let's check and see. So the base, and then we haven't really talked about this either, but the base is this one right here. If you have, for example, heartburn, what that heartburn is you have a lot of acid in your stomach. This is the acid right here. So if you have heartburn, you put a base like Rolaids or Tums or something like that in your body, and that neutralizes the acid in your stomach. Now let's check and see if that's enough to neutralize it. So we've got 5 grams of the acid. We've got 24 grams of the base. So really, again, we're just going to go from one to the other. So 24 grams of MgOH2 has a mass of 24.3 plus 32 plus 2, 58.3 grams in 1 mole of MgOH2. And then from my balanced equation, 1 mole of Mg, and I'm running out of room, I'll leave out the OH2, is going to react with 2 moles of HCl. And then from my balanced equation, 1 mole of HCl has a mass of 35.5 plus 1, 36.5 grams. So 24 divided by 58.3 times 2 times 36.5 equals almost exactly 30 grams of HCl. So that means that if you have 24 grams of magnesium hydroxide, it will neutralize, or it will react with up to 30 grams of hydrochloric acid. Well, we've only got 5 grams of hydrochloric acid. These 24 grams will react with up to 30 grams of hydrochloric acid. So is this enough base to react with all of the acid? Absolutely yes. It's actually 6 times the amount of base you would need. So you would only need 4 grams of magnesium hydroxide to react with all of those 5 grams of hydrochloric acid. All right, so we've done a couple more problems. These 2 dealt with limiting reactants. The first few dealt with just regular stoichiometry problems. If you're still struggling with stoichiometry, let's talk and let's figure out some other things that we can do, maybe just work individually, you and I together, to help you figure out what we're missing with stoichiometry.